Okay, are we in? Guess we are. So, just um, let me check for a second and we will start off immediately. Yes, today we got a lot of stuff to do and not much of time to waste, so yeah. Okay, let's go. Start. What are we starting with? I guess the homotopy of paths. So previously we have looked at um, the homotopy of maps in general, homotopy of spaces by homotopy equivalence maps. And now we are looking at homotopy of paths. Wait a sec, let me just grab the book. Yeah, okay. So we will be reading from both Hatcher and Moncrief from time to time. Let's see. Fundamental group, induced homomorphisms, okay. Let's see what Hatcher has to say, first of all. Algebraic topology can be roughly defined as the study of techniques for forming algebraic images of topological spaces. Most often, these algebraic images are groups, but more elaborate structures such as rings, modules, and algebras also arise. The mechanism that create these images, the lanterns of algebraic topology, one might say, are also formally known as functors and have characteristic feature that they form images not only of spaces but also of maps. Thus, continuous maps between spaces are projected onto homomorphisms between algebraic images. So, topologically related spaces have algebraically related images. With suitably constructed lanterns, one might hope to be able to form images with enough detail to reconstruct accurately the shapes of all spaces, or at least at large, an interesting class of spaces. This is one of the main goals of algebraic topology, and to a surprising extent, the goal is achieved. Of course, the lanterns necessary to do this are somewhat complicated pieces of machinery, but this machinery also has a certain intrinsic beauty. The first chapter introduces one of the simplest and most important functors for algebraic topology, the fundamental group. So, in short, what he is talking about is when you get some kind of a topological category, let's say you consider um, you consider just the simplest topological category, top as in the category of all topological spaces. That is also possible, but usually for for some of the algebraic consideration, at least for homotopy or base point loop homotopy and all that, you consider the pointed topological spaces, top star, and from that you take a functor to the category of groups. Now, many such functors exist, one of them being the pi1 or the fundamental group functor, and there are also, like, for each natural number n, there is a pi n functor, which is the nth homotopy group of a topological space or pointed topological space. So that is the functor. I'm not exactly sure about homology, but you take some kind of a topological category. Either it is H top or top star or H top star. I'm not entirely sure about that, but it is a functor to the abelian groups. So that is that. Those are your Hn. There is a functor for each n in natural number, each abelian, the nth homology group, and all of that stuff. So what we do is we transfer data from topological language to the language of algebra, and there, since algebraic structures are way more rigid and well analyzed, well understood, well behaved than topological structures, we extract some of the data from the algebraic structure, and yeah, we deal with it that way. So, okay, um, just wait up a second. Just wait up a second. Just a second. Okay. Okay. Looks fine. Looks fine. Okay, back to the stuff. Just another second. I remember there's another thing to do. I should really finish these things before starting the live, so there's minimal interruption. Yeah, okay. Let's go. So these are the algebraic functors from some kind of a topological category to some kind of an algebraic category. Sometimes there are functions to sometimes there are functors from some derived category of top to, let's say, rings. Sometimes non-unital rings, sometimes algebras. There's all kinds of stuff. So today we'll be mainly focusing on this one functor and what exactly this category is. So that is it. So pretty much everything we do today will be based on this functor, and we also will be at first looking at this category, h top. Actually, we have looked at this category, that is the homotopy of maps. So that category contains morphisms being classes of homotopy of maps. So there is that. Today we look at homotopy of paths in short, then the main thing, loop homotopy, and then we get to, I guess, hopefully the fundamental group, and there's that. There are some terms about all the fundamental groups of the circle and all of that stuff. We will not probably be able to look at Van Kampen's theorem today, but that's okay. That's pretty far anyway. Yeah. At first, let's just read from Hatcher what is written here. The idea of the fundamental group. To get a feeling for what the fundamental group is about, let us look at a few preliminary examples before giving the formal definitions. Consider two linked circles, AB in R3, such as this. Okay, so he considers these two circles, let's say like that. Yeah. So I guess the linking and the stuff is understandable from this image. Let's call this A, let's call this B. So we look at two circles like that. It is impossible to separate A from B in any continuous motion of B, such as pushing, pulling, or twisting. So at best what you can do is tug at B like this. So okay, not really that. Let's see. So let's draw something like this. So add, oh geez. Let's see. So at best what you can do is tug at B like this. You pull B that way, but it of course will get stuck because it gets stuck right here at A. So that is the link thing in the linked circles. We could even take B to be made of rubber and stretchable string to allow completely general continuous deformations of B, staying in the complement of A at all times, and it would be impossible to pull B off of A. At least that is what intuition suggests, and the fundamental group will be a way of making this intuition mathematically rigorous. So the reason why we cannot take these two things apart is because look at this circle, look at this A. So in this A, B, when you draw the circle B, let's say we make a small gap here. So when you're drawing the circle B, B is essentially always within the complement of A. So B is entirely outside A, and when you suppose you are able to somehow pull the two circles apart, then you also see that B is still outside A. So in this case we saw that B was always in A complement, so B was never actually intersecting A. But in a sense, if you pull this apart, then you have to go from being on one side of this specific part. So B, this part of B, let's see, like this part of B was on one side of A, this part of B went from being one side of A to another side, and in a sense this continuous deformation is not possible, so it after all leads to some kind of a contradiction in terms of some intuitive image of the intermediate value theorem that we are thinking. So this part of B is on one side of A, and then after a continuous deformation we see that it is on another side. And see, since both of these are connected spaces, in some kind of an argument we can say that they must have intersected at some point. So that is the argument, but clearly this is not possible, since in the beginning of the deformation we saw that in the starting situation in the link we saw that B was outside A, so B was in A complement, and in the end we also see that B is an A complement. So nothing really changed that way, so there is no direct contradiction, but there is this sense, this we can see quite intuitively that there is something wrong going on which we needs to address properly. So there is that, and exactly this thing, if we make rigorous, that leads to the notion of the fundamental group. Instead of having B linked with A just once, we could make it linked A 2 or more times, in the figures to the right. So this gets increasingly harder and harder to draw, but I'll try. So what's exactly there? This is like that. Okay, not really. There it crosses itself. So this is a small segment. Then this comes over here. Yeah, it comes over here, right? And goes through this. And yeah, it just goes to that. Yeah, this should be doable. And there is A, which is like this. Let's see. Not the best loops ever drawn in the history of humanity, but at least you can see and understand what is exactly going on. I'll not attempt to draw even more loops because that is just pointless and quite insane. So just for each non-zero integer n, we could have an oriented circle Bn linking this. So this circle is, let's say the loops go this way, not really that, this way. So this is, let's say B2, let's say this was B1, and for each integer n, for each let's say for each positive integer n, we get an oriented circle Bn. In fact, and not just a positive integer n, yeah, it's for each integer n. Yeah. So the way you get a negative B, let's say B minus 1, is you reverse the direction. So B minus 1 is nothing special, it is just yeah, it is just this. B minus 1 is just this. Yeah. So now these circles are going like that, this circle is going like that. So this is B minus 1 around A. And you can repeat this circle. So after all, the minus is not generated by any change in the winding or the loop, because there is practically only one way of linking these two circles in that manner, but the minus comes from the opposite orientation of the map. So suppose you start with one direction. So after what is a circle? Circle is S1, which is, let's say 0, 1 quotiented by this set 0, 1. So that is what a circle is. And let's say points which are less than half are close to this, and points which are greater than half are close to that. That is this that defines this orientation. And in this case, let's say points which are less than half are near this, and points which are greater than half are near that. So that defines the orientation that way. But once you fix a reference orientation, that is 1, you get basically the same thing. This is this exact dilemma of orientation kind of has to do with the automorphisms of the fundamental group, but clearly I'm going ahead of myself, and I should be I would mention this. So this dilemma of orientation. So which direction to choose to be +1 and which direction to choose to be -1 is quite arbitrary indeed, because in space, if you move these two circles around, you will see that you can just flip the circle in a way, and this this counterclockwise orientation would just get, if you, let's say you take an axis like that and you just flip the circle like that, you just flip the entire system. So then what you get is, again, very hard to draw, not does not make it that easy for me anyway, but yeah, let's say something like that, and the orientation will be like that. And you see, that is exactly what B1 is. So from -B1 to B1 you can go by just applying transformation to the ambient space. That is not something which uniquely determines an orientation, but yeah, so we will see that this kind of a transformation of the ambient space is has to do with the automorphism of the fundamental group, let's say pi1 of S1. So the structure of this thing, the more trivial it is, the more simple it is to determine the orientation and determine the orientation uniquely. But yeah, that is what we will see going forward. Where by a circle we mean a curve homeomorphic to a circle. Yeah, so topologically everything is up to homeomorphism. To complete the scheme, we should let B0 be a circle which is not linked at all. So yeah, this is very easy to draw. I can draw this. So this is this. This is B0 with respect to this A. This is B0. Let's just make this homeomorphic to a circle. Yeah. Now, integers not only measure quantity, but they form a group under addition. Yeah, that is what we are kind of getting at. A group operation can be mimicked geometrically by some sort of addition operation of oriented circles to link A. Okay, so B1 plus B2 can be deformed to the loop. So this is like, let's say you have the A here. I'm not going to bother drawing all those crossing gaps and all that, because that's quite tiresome and frankly quite unnecessary. So let's say you start with the base point here, you draw a B1, which let's say goes like this. So that was a B1, and after that you draw a B minus 1, let's say, which goes like this, B minus 1. So with that, what you essentially did was that you went like that, then went like that. Okay, so yeah, that's where I have made the cardinal mistake. B minus 1 should be like this. So you pass below the circle and then come from top of it. So what you did is you went below the circle, then returned up from below. So what indeed happened, if you remove the fact that these two segments actually start from the base point and reach the base point, then you can slightly deform this loop to look like this, yeah, so that after that kind of deformation looks something like this. You go over this, go below this, then again pass below this, and again return from top. And this, as you can see, is let's say, probably I should draw it in a slightly better way, which is like this. You start at the base point, go over this, pass below like that, then again pass from on top of that, and then return to here. This is the base point. So this is in some way this loop is in some way some kind of an addition of b1 and b minus 1, and you see that you can just shrink this loop this way. So this loop is nothing but the trivial loop, which is b naught. So in some sense, this sort of an addition of loops can take place, where essentially your addition of loop just is just the addition of integers. It is just the addition of integers. This is the addition of loops in the scare codes. So this we see that from going from the loop space B, the space of all loops, we are moving to the addition of integers. So that is the kind of group structures the loops have here. Yeah. Now, integers not only measure the quantity, that. So more generally, we see that bm plus bn can be deformed into bm plus n for arbitrary integers m and n. Now that in forming the sums of loops, we produce loops that pass through the base point more than once. This is the reason why loops are defined merely as continuous paths, which are allowed to pass through the same point many times. So if one is thinking of a loop, something made of a stretchable string, one has to give the string the magical power of being able to pass through itself unharmed. However, we must be sure not to allow our loops to intersect the fixed circle at any time. Otherwise, we could always unlink them from A. So, okay. Next, we consider a slightly more complicated sort of linking involving the three circles. Okay, this sure looks pretty dire. This will be a nightmare to draw. Telling you. This is a nightmare to draw. This is something like as follows. This part, and then this part. B goes like this, I guess. Okay, B goes like this, and C goes like this. Something like that. So like, can you exactly see what is going on? I bet you can't. Okay. You have one circle, have another circle. Like that, I guess. Oh, come on. What is the next linkage? It passes through this gap and it passes through this gap. The problem is that there is no simple way of drawing that circle, because whatever I do, there will be linkages I will not be able to maintain. Let's say it's something like that. Yeah, I tried my best to get this. Yeah, I guess that works. That is the best I can make it work like. So this is A, this is B, and this is C. As you can see, B is entirely above A, so we can pull B apart from A and pull A and B apart, and then what it looks like is this, that there are just two completely disjoint circles, and there's something going on between them. And what happens between them is quite unholy, to be frank. So it looks like this. Thankfully, Hatcher has drawn that for me. Okay. I should draw this again, perhaps in a more prominent way. I should try to not cause self loops. That is a bit problematic. Yeah, something like that. So this is where the loop passes below that. And here as well. Here. So this is some kind of a double loop of a circle. So here we have two circles and there is one loop going around it, and you can repeat the number of times this crossing happens. So that is another thing. Next, we consider a slightly more complicated sort of linking involving three circles forming a configuration known as Borromean rings, shown on the left of the figure. Interesting feature is that if any one of these three circles is removed, the other two are not linked. Yeah, that is the thing. That as you can see, that C is not exactly linked with A if B is not present. So if B was not present, you could move this part of C around here, and slide this back, and then you can just pull C apart from A. And similarly, we have already removed B from A, and if we somehow just remove this circle C, then this loop C, then we can separate A and B completely. So there is that. The other two are not linked. In the same spirit as before, let us regard one of these circles, let's say C, as a loop in the complement of the other two, and ask whether C can be continuously deformed to unlink it completely from A and B, as always staying in the complement of A and B during the deformation. We can redraw the picture by pulling A and B apart, dragging C along. Then we see that C is winding back and forth between A and B, as shown in this figure. In this new position, we start at the point C indicated by the dot and proceed in the direction given by the arrow. So let's say the base point of the... Okay, very nice. Let's say this is the base point of the loop. Then we pass the sequence forward through A. Look, I don't really follow what forward and backward mean anyway, so whatever. To get a more accurate measure of how C links with A and B, we regard the four parts 1 and 4 in an ordered sequence. So okay, this I can perhaps show is that you take this loop and you pull it entirely back to the base point before doing anything else. So do something like that. This goes through there, then you pull it to the base point again, then you send it back to the loop, and then it goes like that. So the loop that you consider afterwards is that something that starts at this base point, goes back here, then again starts at the base point, goes back here, then again starts at this base point, goes back here, and once again starts from this base point and goes back here. So it is 4 loops, and what you can see here is that this loop goes below A and then above, on top of A. So let's say this we call a plus A, and then this loop also goes below B, and then after that above B. So let's call this plus B, and then you see that this loop goes above B first, and then below above A first, and then below A. So this would be a minus A, and this loop also goes let's see, this loop goes above okay, this is going twice. Okay, this loop goes above B first and then below B, so that would be something we call minus B. So this loop is basically just A, then a B, then a minus A, and then a minus B. And in a way this notation is bad because this tempts us to cancel this, but these operations are of course not commutative. So a better way to notate it would be something like this: AB, A inverse, B inverse. Again, represents a composite loop, AB, A inverse, B inverse, where A and B are loops linking A and B. But from the picture on the left, it is apparent that C can actually be unlinked completely from A and B. So in this case, the product AB, A inverse, B inverse should be trivial. Can C actually be unlinked from A and B? Maybe, I got no clue. Okay, so he actually changed the example a bit. In this case, the circles A and B are actually linked. So it looks something like this. Okay, that is what A is. Then I get C, which is like this, and in the end you get B, which looks like this, I guess. So in this case, what's exactly going on even? Okay, I see it now. So one thing you have to notice is that C is completely above B in this modified example. So if B is here, C goes entirely above B. Okay, C goes entirely above B, and also that C is entirely below A. Right? C is entirely below A. So what you can do is just pull C up like this. You pull C up, and let's say at some point you pass it under A. Let's say something like this, and you pull it more and more upwards, and then you can see that you can just bring C out of this linkage. So C is indeed not linked here, and after doing this process it would look something like this, that C, you have unlinked C, or that it was not even linked at the first place, and then you have A and B linked like this. So in this case, these loops, however way you draw it, they should be trivial. So this guy should be just the identity loop, or E. So this group of loops should be commutative. So that would be of the form MA plus NB. So this would be just commutative. So this is indeed what one would call Z square being the fundamental group of it. And in the previous example, this would someone would say that Z star Z is a fundamental group of it, or which is in a better way known as the free group generated on two elements. That is probably the better way of notating it. But anyway, the fundamental group of the space X will be defined so that its elements are loops in X, starting and ending at a fixed base point X0 in X, such that two such loops are regarded as determining the same element of the fundamental group if one loop can be continuously deformed to the other within the space X. All loops that occur during the deformations must also start and end at X0. So yeah, what we are doing here is that the spaces where these loops are not really so these spaces are not really A and B, the circles themselves. So the loops are actually present in the following space. The loops are actually present in A union B, or let's say A disjoint union B. So the loops are present in this space, and we are talking about the fundamental group of this space actually. So it is entirely the complement of A union B. Let's say these are embedded in R3, so R3 minus A union B is the space that we are looking at. And similarly in the previous case, in all of the previous examples, it was the ambient space R3 minus our loop space, our circles and rings that we considered. So this was really the group that we were considering. Yeah. Just wait a second. So yeah, it was the cat at my doorstep again. So there's that. Yeah. Okay. That was a lot of talk about the loops. Now we get to paths and homotopy. And before starting, I'll just look at what is going on in Monkrus, because that is probably a more definitive book than Hatcher. So one of the basic problems in topology is to determine whether two given topological spaces homomorphic or not. Blah blah blah. Showing that two spaces are homeomorphic. Yeah, the long line R. Topological properties were studied up to carry very far in the problem. Okay, great. Simple connectedness. Fundamental group of the spaces. In this chapter, we define the fundamental group of and study its properties. Then we apply it to a number of problems, including the problem of showing that the various spaces, such as those already mentioned, are not homeomorphic, as in the torus, circle, sphere, and disk. Other applications include theorems about fixed points and antipode preserving maps of the sphere, as well as the well-known fundamental theorem of algebra, which says that every polynomial equation with real or complex coefficients has a root. Finally, there is the famous Jordan curve theorem, etc. Homotopy paths. Before beginning with the fundamental group of a space, we consider paths on X and an equivalence relation called path homotopy between them. We shall define a certain operation on the collection of the equivalence classes that makes it into what is known in algebra as a groupoid. If F and F dash are continuous maps of space into the space Y, we say that F is homotopic to Y. Okay. So the Monkrus defines homotopy of maps. We think of a homotopy as a continuous one parameter family of maps from X to Y. If we imagine the parameter T as representing time, then the homotopy F represents a continuous deforming of the map from F to the map F dash as T goes from 0 to 1. We consider a special case of this in which F is a path in X. Recall that if F, so a path is just a function from 0 to 1. So what really is a path? A path is nothing but a function from closed 0 to 1 to X. So that is path in X. So dealing with path homotopy is not really different, because in that case when we looked at homotopy of maps, we were essentially looking at continuous functions from, so a map was basically just this, and a homotopy was this X cross I to Y, and a homotopy of paths in this case will be something like I cross I to X. So there's that. And yeah, so path homotopy is something not really new or different from what we have done before. Two paths F and F dash mapping the interval I equal to 0, 1 to X are said to be path homotopic if they have the same initial point and the same final point. Okay, yeah, there is one difference in path homotopy. There's one small difference in path homotopy, is that uh, this we considered in case of map homotopy of maps, we considered that any continuous function f from x cross I to y would be qualified as a homotopy. But in case of path homotopy, we fix the points x0 and x1, which are just f of 0 and f of 1 respectively. So we say that f of 0 comma t is the same point for all t. Let's say this is x equal to x0 for all t and I, and x1 equal to f of 1 comma t is the same point for all t and I. So that is the only other condition in path homotopy that we require, which we did not have in case of just homotopy of maps. So there is that. So then you can show that this homotopy of paths is an equivalence relation as well. So given two paths, p1, okay, yeah, not really that. This relation, homotopy of paths, is an equivalence Let me just look up if there is a particular topological category which considers only path homotopies, because it certainly looks very promising, and indeed the machinery looks good, to say the least. Okay, so that is exactly what the fundamental groupoid is. Very nice. We will be looking at the fundamental groupoid How much time do you have? We have almost 2 hours. That's good. That is just enough time to cover the stuff. Okay, certainly looks promising. So yeah, we'll be dealing with these things in a slightly more algebraic way than treated in the books, because we live in modern times and modern times require modern methods. Let's see what Hatcher says. The fundamental group will be defined in terms of loops and deformations of loops. Sometimes it will be useful to consider more general paths and their deformations. By a path in a space, we mean a continuous map f from I to x lies the unit interval 0, 1. The idea of continuously deforming a path keeping the endpoints fixed is made precise by the following definition. Homotopy of paths is blah blah blah, says that. Okay. When two paths f0 and f1 are connected in this way, they are said to be homotopic, linear homotopies. Any two paths f0 and f1 in Rn have the same endpoints x0 and x1 are homotopic via the homotopies, etc. Okay, during this homotopy each endpoint travels. So, okay, we will be looking at exactly what is going on in Rn. The relation homotopy of paths with fixed endpoint in any space is an equivalence relation that is there to prove. We take the product of paths. Pi 1 of x comma x0 is a group with respect to the product. Okay. The set of all homotopy classes of loops at a base point. So we suddenly go from path to just the base point. Then we consider, okay, so we prove that pi 1 is a group indeed, and then we calculate the homotopy group of the fundamental group of the space Rn. It's natural to ask about the dependence of pi 1 comma x0 on the choice of the base point. Okay, change of base point. Change of base point gives an isomorphism. A space X is simply connected if there is a unique homotopy class of paths connecting points. Okay. Fundamental group of the circle. Deal with the fundamental group of the circle. Every non-constant polynomial. Okay, so then we look at a proof of the fundamental theorem of algebra as usual. Why does everyone do it? Why? Okay, anyway. Torus, look at the fundamental group of the torus, induced homomorphisms. So we are now really talking about the functor, the fundamental group functor, and then there is the exercises, and then we see Van Kampen's theorem. That is what Hatcher does. What does Moncrief do? Moncrief exactly deals with the fundamental group, first homotopy group, then we get simply connected space, homomorphism, and then we, I guess, leave into covering spaces. So okay, see what is to be done, and what is to be done will be done. How exactly to approach this? So let's first create a route map of what we are going to do. We are going to define let's see, homotopy of paths, homotopy of paths, then that it is an equivalence relation. That is basically not really a different step. Then we will just look at the fundamental group of it. I can't resist looking at it. Fundamental groupoid. There's that. Then we look at, since this is a groupoid, then we look at the fundamental group. So here we'll have to make the transition to talking about loop homotopies. And there we'll be talking about pointed spaces and the category top star. And from there we'll be just looking at the fundamental group directly. So I guess that should be the route map that we are to be following right now. Okay, so let's get this going. So first up, we define homotopy of paths. Homotopy of paths. First we define what a path is. And we define a path in terms of its two endpoints. So we specify the two endpoints and then we define what is meant by a path between the two endpoints. Given endpoints, or just given points x0 and x1 in the space X. So yeah, first of all we fix the topological space X. So this we are dealing in the category top currently. Currently we are just in top. Given 2 points x0 and x1, a path from x0 to x1 is a what is it? A path is a continuous map. I will try my best to actually avoid the word continuous. We'll never mention continuous maps again, because we assume every map is continuous, as we are doing in our top. Is a map f from I to x. Such that f of 0 is x0 and f of 1 is x1. So that is it. That is what a path is between any 2 points. When do we say 2 paths are homotopic? So defining the homotopy relation between paths. Again, given 2 points, given x0 and x1 in the space, and paths f and g both from x0 to x1. So what that means in quotes is that f and g are maps from I to x, such that x0 is just f of 0 is g of 0, and x1 equals f of 1 equals g of 1. So I know this is not very visible, but I chose that particular color because it is not very visible. We say f is path homotopic to g if and only if there is a homotopy. If and only if there's a homotopy f from I cross I. So it is just a map from I cross I to x, such that f of 0 comma t equals x naught for all t, and f of 1 comma t equals x1 for all t in I, of course, and f of 0 is just f of 1 is just g. So that is what we mean by two paths being homotopic, so that their endpoints are preserved always, and there's a homotopy which connects these two paths. So there is that. Why is it an equivalence relation? On the weight of being an equivalence relation, every path is homotopic to itself. Actually I made a slight mistake here. There should be this comma 0, this comma 0, and this comma 1. That is the actual notation. Homotopic to itself. We say that f of t comma s equals f of t for all t in I, and that just clearly defines a homotopy. If f is a homotopic to g, then g is homotopic to f, because given this homotopy f from I cross I to x, such that this is a homotopy from, let's see, f of 0. The first map is f, and the last map is g. Then define the homotopy like this. Then define a new homotopy define this homotopy by g of t comma s equals f of t comma 1 minus s for all s and t in I. Yeah, so you can check for yourself that defines a homotopy from G to let's say to F, and if F is homotopic to G and G is homotopic to H, and suppose there are these homotopies F and G which are defined in analogous ways. I'm not going to make a real fuss about it. We can define a new homotopy. We can define this new homotopy H from I cross I to X by H of S t comma S being equal to F of t comma 2s if S is basically just less than equal to half, and f g of t comma 2s minus 1 if s is greater than equal to half. So what this requires probably some explanation. So given these base points, given these endpoints x0 and x1, so there's a path like this, there's a path like that, and there's a another path like that, f, g and h respectively, and suppose there is this homotopy going from F to G, and then this homotopy going from G to H. So what we do is, within the span of S going from 0 to 1, within 0 to half, we cover this entire homotopy from F to G. So for that we will have to speed up so that this goes in 2x speed, and then from G to H we'll also have to go in 2x speed, but we also then have to start with 0. So this is the formulation that exactly does that, and this is the kind of thing that we'll be coming back to over and over. That is it. Show that this path homotopy is also an equivalence relation. So what we do is, what we now observe, make an observation that given any 2 points, given any 2 points x0 and x1 in X, let's see. I will denote this by we define the path space between these 2 points. So we consider the set of all paths between these points. What should I actually denote this by? Yeah, let's keep it simple. Let's just call it P x0 x1. Yeah, we define this to be the set of all paths from x0 to x1. This such that f of 0 is x0 and f of 1 is x1. Let's say we call this the path space. So this is not really a space as such. Okay, we don't really need to call this anything. Then this path homotopy equivalence, this path homotopy is an equivalence on this set, on P x0 x1, and given any set and an equivalence relation on it, we can have the quotient. So we take the quotient and this is the thing that we have between any 2 spaces, inside any space between any 2 points. So yeah, I guess the most natural thing to do is now get away with all this hesitation and just define the fundamental groupoid. Yeah, let's just define the fundamental groupoid. So just as a reminder, a groupoid is a category where all morphisms are isomorphisms. Okay, so that is what really a groupoid is. A groupoid is a category where all morphisms are isomorphisms. So we define the fundamental groupoid by this. We call it pi1 of the space X. So this is capital Pi, this is not small pi. Given space X in the category of topological spaces. So we pick a space X in top and define a category given any topological space X. Define a category called pi1 on X by the object of pi1 of X, being equal to just the set X. Or what you can do is you can just pull this X to the set, so the set of X. So it is just the points, it is just the set of points in X. So this is the object, and for any 2 points, x0 and x1 in this object class, in fact in this object set, because this is a set, right? So for any 2 points x0 and x1 in this object set, we define the morphism set to be the hom set, of, let's say, I'm not writing the category name below because it's very cumbersome. We define hom of X to be exactly that thing, P of the basically set of all paths from x0 to x1, but you quotient them by the path homotopy relation. Or if you want, you can just distinguish this from the usual homotopy by writing a P below it. So yeah, that is how we distinguish, writing P. But we define the hom set to be this. So what is really going on here is that a morphism from x0 to x1 is an equivalence class, of path homotopic paths, of course, paths from x0 to x1. So that is what a morphism is. Now up next, what we have to prove: show that this pi1 of X is indeed a groupoid. Which basically means that for any points x0 and x1, note that they can always be just the same point. So we could be considering loops here, but we do not explicitly say that we are considering the loops. We will just separate this out later on. Just wait a second. So yeah, for any 2 points in X, we have to show and any F from x0 to X, or let's denote this by P. Any path from x0 to x1, there is a path P dash from, or let's call it Q from x1 to x0, such that P composed with Q. Okay, so there's the catch. We have defined morphisms, but we have not really defined the composition. Okay, my bad. I guess we have to define the composition. But yeah, so this show that thing exists. Let me just put this down first. Equals the identity path on x0 and PQ. That was what I was thinking, that I was missing something. Like there was something which was just not here. Okay, let's move this. Wow, that was great. That was hilarious. Let's move this here. Let's put this back, I guess, like that. Yeah. Define composition on this hom set, which for some reason I am rather inclined to denote by this, because it really makes it more clear exactly what it is. Define composition. So given path P from x0 to x1, actually define composition on this category. Actually, what I've been doing, define composition on this category for this path from x0 to x1, and another path Q from x1 to x2. We know that P is of course an equivalence class of paths, and Q is also an equivalence class of paths under this path homotopy relation, such that F is, again, the F and G both are maps from I to X, such that F of x0 equal f of 0 is equal to x0, G of 0 and F of 1 are both x1, and G of 1 is x2. And what we do is define H to be a map like this. Define H to be f of just 2t and g of 2t minus 1 if t is less than equal to half and if t is greater than equal to half. And define Q, let's call it star P, to be this equivalence class of H in this hom of x0 and x2. So that is what we define it to be. And as anything, as like pretty much all of the things defined on some equivalence class, we show that this composition is well defined. what is required for the composition to be well defined? Well, this is going to be a bit wordy, so I have to move this again. Yeah. Suppose f0 and f1, we just take these maps. We just take the maps f1, f2, g1, g2 from I to x, such that the equivalence class of f0 is the equivalence class of f1. That is to say that f0 is homotopic to f1, and sorry, not f0, f1 is homotopic to f2, and g1 is homotopic to g2. Then let h1 be defined by the same thing, h1 of t be defined by f1 of 2t, and g1 of 2t minus 1, t less than equal to half, t greater than equal to half, and let h2 of t be defined by f2 of 2t, g2 of 2t minus 1, t is less than equal to half, t is greater than equal to half. We show that h1 is homotopic to h2. That is it. Okay, so that is the thing. Suppose we have been given homotopy f is the homotopy from f1 to, let's say, f2, and g is the same. Similarly, g is the homotopy from g1 to g2. Then define the homotopy h. Then define homotopy h to be from, let's say, h1 to h2. That is what we want. By, how do we define this homotopy by? We say that h of t comma s is equal to, check this out, f of 2t comma 2s and g of 2t, I think. Yeah, g of 2t comma 2s minus 1. G of 2t or 2t minus 1. I'm not really sure about that. So yeah, let's just draw this out. What can we even do other than that? Let's see. So this is f1, this is f2, this is g1, this is g2, and this entire thing is h1, this is h2. So what we do is, yeah, so this also should be g of 2t minus, or should it really be that? Should it really be that? S should be what S is. S should remain constant here. Yeah, I think this works. Less than equal to half, t is greater than equal to half. Yeah, I guess this works. That is because suppose this is another map. This is another map. Let's say h of comma s. So this is the S map. So this should be going through first of all f of comma s, and then it should be going through g of comma s, and it should go in double speed through both of these. So yeah, we define the homotopy by like that. I'm sorry. So we define the homotopy like that, and therefore we see that the class of h1 is equal to the class of h2. So indeed qp, or rather q star p, or like categorically we just denote it by qp, but in probably in reality we'll be denoting it by q star p, or sometimes even g star f. Oh no, actually it is denoted f star g. Yeah, it is f star g, but categorically it is actually q star p. So these are the same thing as such. I have no idea why they decided to denote it by f star g. That makes seriously no sense. But anyway, what can we even do? So whatever this thing is, this is uniquely defined. So this is uniquely defined. We showed that this is indeed a category. So yeah, okay, this is not really a category in that way. We have not shown. Okay, let's define the identity, because we need the identity for the next proof. So next proof is just getting delayed and more delayed. What can we do? We just need to take everything a bit slowly. To show this category, up next we need to define the identity. What is the identity morphism in this case? So since all of these morphisms are, these are all equivalence classes of the paths. So the identity path would be, let's see, id sub x naught should be the path of the identity map, or the should be the class of the identity map x naught. So recall that this identity map is from x to x naught, such that this evaluated at any point t, so this sends any point t to x naught. So that is what it really is. So this identity morphism is really the class of the constant map. So identity is the class of the constant map. Okay. So there's just one thing left, which is associativity. So we have to show that R star Q star P is equal to R star Q star P. This is probably the most boring thing one would have ever done in their lives. and I just want to skip it. But I won't skip it for just one reason, is that we have to construct this by maps. So I'll just do the construction by maps. Let's say from x0 to x1 you have got this is very bad, this is just extremely bad. You get f1, you get f2, and from x1 to x2 you get g1, you get g2. From x2 to x3 you get h1, you get h2. So on one hand, r star q star p, so r star q is really the equivalence class of on one hand it is of h1 star g1. That is because we are just extending the star notation to the maps, so that the same way we defined h here, so that this we define to be g star f, because there is not much of a better way to simplify the notation other than doing this. So r star q is really this, and h1 star g1 is this map, which is h1 it is g1 of 2t for half the time, and it is h1 at double speed for the other half of the time. So h1 star g1, if you start that with f1, that would be equal to a crazy thing, which is okay, so this is like g1 of 4t for t less than equal to 1/4, h1 of 2t minus 2, or rather 4t minus 2 for t is less than half and greater than a fourth, and this is f1 from f1 for 2t minus 1 for t is greater than or equal to half. Now on the other hand, h1 start with g1 star f1, that is equal to this map. It is getting messier and messier, but yeah, okay, we can deal with it. How can we? Just wait up a second. What exactly is going on? Are we writing things properly? This guy goes from x1 to x3, and this guy goes from x0 to x1. Yeah, I guess it checks out. This guy goes from x0 to x2. Yeah, this really checks out. Are we missing something here? Yeah, we are entirely missing this. Oh geez, okay, this is wrong. So f1 should come first, f1 of 2t when t is less than equal to half. Okay, and then is h1 star g1 of 2t, and we just copy down the definition of whatever that is. That means 4t when t here is less than equal to 3/4 after half, of course, and h1 of 4t minus 2t. Okay, not really that, we are still even more doomed. So it was 2t minus 1, so it should be 4t minus 2. 2t minus 1 is 40, it should be 40 minus 3 here. Okay, the people say the details don't matter, and I also believe the same, that the details don't really matter that much. But when we are doing it for the first time, I think we should be just a little bit careful about the details, because it it works out in the long run after all. Okay, this is t of f1 of 4t. T is less than or equal to quarter. G1 of 4t minus 2, I think. Yeah, it is 4t minus 2. T is less than or equal to a half. And just h1 of 2t minus 1. T is greater than or equal to a half. So these two are the different maps. And it is not immediately obvious why there is a homotopy between them. But as you can see, it is just a different kind of a partition. It's just a different kind of a partition. So on the homotopy, let's create the I cross I square. So this is the I cross I. On the first map, from H1, G1 and F1. Oh, okay. There's this trouble that there should be H2, G2 and F2. And these all indices should be 2, not a 1. This is the different thing. So this looks like this. And on top, this looks like this. So what we really have to do is that we have to do this. And while this homotopy is going from... Okay, I messed this up again. So suppose we are going from top to bottom. This from F1 to F2. This is from G1 to G2. This is from H1 to H2. So you have to comfortably deform the homotopy of the F slightly, deform the homotopy of the H slightly, and then so we can reconcile with that. So this is what we are really doing on the I square. We have to somehow make sure that this part happens, and it is not necessary that these partitions are these smooth lines. This could be practical anything, as long as these are functions, satisfy the horizontal line test in this case, or whatever that is. So this we define. We got the homotopy, right? We got the homotopy. We got this H1, the class of H1 star G1 star F1 equals the class of H2 star G2 star F2. And yeah, that shows the associativity, shows the unique existence of identity maps, and composition exists, and I don't think there is much else to be shown about this. So what else is now remaining? So we showed that the fundamental groupoid capital pi 1 of x is indeed a category. What we now need to show is that it is actually a groupoid. For that, we need to show that every morphism is an isomorphism. For that, for any morphism, we need to come up with basically the inverse map. So do it like this. Suppose P is the equivalence class of this map F, where P is the equivalence class of F, and this is a morphism from x0 to x1, where f of 0 is x0, f of 1 is f of 1 is x1. Define f dash to be again a map from I to x, such that f dash of 0 is x0, rather x1, or rather we can just say f dash of t is f of 1 minus t. So that is how we define it. And we also define f q. We define q to be the morphism, q to be the class of f dash, which is a morphism from x1 to x0. Now what remains to show is that qp or q star p is equal to identity on x0 and p star q the identity on x1. So that is not very difficult, given that qp, I'll just write qp, I'll just do with the star. qp is equal to the class of f dash star f, right? Now what does f dash star f do? Okay, so this is the class of f dash star f, which we need to show that this is indeed the class of the constant map x0. I'll just show this one thing, because the other is exactly the same argument and it is written the same, it is the same, it's just it just goes different way on the other direction. So we have to show that this is the class of x0, as in the class of the constant map x0, as in we have to show that f dash star f is path homotopic to the constant map x0. How does one do that? Well, first let us write down the definition of what exactly is meant by f star f at this point t. It is equal to f of 2t, t less than equal to half, and it is f dash of 2t minus 1 for t less than equal to half. What we do with the homotopy, define homotopy f from I cross I to x by, so what is going on here is that there is this path, one way we are traveling like this and the other way we are traveling like that. So what I wish to do is just we go halfway around, we just don't go full way, we go halfway around and stop here, then come back from here, and as s approaches 1 we just don't move at all. So that is kind of the idea. I don't know if saying that out loud like this makes sense, but the formula we write down is this. So so suppose s is like this. Okay, just wait a second. We draw the square. That's not a good square. We draw the square of the homotopy. This is the square of the homotopy. This is, let's say, the t axis, and this is, let's say, the s axis. So here all these points are x0, right? All of these points right here, these are all x0, and all of these points right here, these are all x1. So what no, not at all. this is also x naught. So initially this is f dash star f, and in the end this is id, or this is the constant map x naught. So all of these points are x naught as well. All of these points are x naught as well. So what we do is, let's see, we kind of apply an identification on this square. So since all of these points are the same point, we identify this entire line to be one point. So what we get is something like this. We get a triangle, right? So the initial map is f1 star f from x naught to x naught. In the middle somewhere here is supposed to be x1. These, now notice that these two sides, these also just represent the same point x naught. So what we can do here, in this we identify the top edge corresponding to the constant map. On this one, we identify the sides which are all just that one point x naught. So that would look like taking this side and placing it on top of this, like that. So that would look something like a cone basically, right? Why did I just put that cone upside down? This cone's looking like this. So suppose we are looking at this cone from the bottom up, and this one entire side, is just x naught. This point is x1, and we just never go to x1 again. So now we orient this cone properly, orienting the cone in space. How we orient it is, look, this is the axis of the point x naught. In the end we stay at this, in the end, or rather I should just make this line a bit bold. In the end we stay at this point as a constant map. Initially we go out and then we come back. This point is x1, and we just never go that far again. So all of these levels are like that. And now we put the axis back. So this is S, and this is T, and this is half. Suppose the T axis has been looped like this. The T axis now looks like this. This is 0, this is 1, and this is half. The half is here at x naught. So as S progresses, suppose this is the value of S here, and if we just place this on the xy plane like that, something like that, if this is half, this is the frontal view of the cone, this is S, this point right here, I think it would be something like, let's see, what would it be? This point would be 1 minus S, right? This would be half of that. So okay, this will be half minus S by 2. This will be half minus S by 2. Yeah. So this is up to where we go, and then we stop here, and then we start again going back this amount of time. So what we do is, uh, in this homotopy f t comma s, that would be equal to the following. We go along f dash star f for how much time? We go along it for this much time, half minus s by 2, not really, for how much time? We'd be going along it for the time t. If t is less than equal to half minus s by 2, we would be staying at that point. We just halt at that point, half minus s by 2 until t grows enough up to, let's see, half minus s by 2 this way, half minus s by 2 that way. So that would be something like, oh okay, what would that be? So this is the length of 1, this is half minus s by 2, 1 minus s, that would be what is it? This amount is half minus s by 2, this amount is half minus s by 2, this amount is s, so half plus s, yeah, up to t is less than equal to half plus s, and this would be f dash star f of t for t greater than equal to half plus s by 2. Whew. Okay, so I guess that is what it is. So indeed, this is a homotopy from this is a homotopy. We have defined a homotopy, and we can write it in even a better way, because during the first half it will be all f in action, so it will be all f of 2t, where t is less than equal to half minus s by 2. We would just be standing at f of the point f of 2t, or let's see, the f of 1 minus s. Okay, so that is there is this okay, so that is one issue. What is this point? F of 1 minus s, is that equal to f of s, f dash of s? Yeah, that is indeed okay, yeah, sure, yeah, sure, no problems with that. So this is f dash of 2t minus 1 if t is greater than equal to half plus s by 2. So putting it there, that would be just equal to f of s, f dash of s. Yeah, for this is for the time that t is half minus, half plus, half minus. This is half minus s by 2 less than equal to t less than equal to half plus s by 2. So this is the definition of the homotopy. So we define the homotopy by this definition. This would really be well suited for an animation by someone like 3 Blue and Brown. Grant would really do this the justice, but I guess through this identification procedure we can see exactly what is going on, or perhaps we cannot see it, is all in my head. I'll try to make an animation, I'll try to animate it someday. That would be like absolutely one of the best things I'll be ever doing. But yeah, so we have a homotopy from f dash star f with the constant map x naught. So as you see here, if s is equal to 0, we see that this part is exactly eliminated because t at t is equal to half, these two exactly match up and we get this. And if s is equal to 1, then for this is the entire time being. If s is equal to 1, this is the entire time for t equal to 0 to t equal to 1, and we see that we just stay here. This is just equal to x naught. Oh no, this is not equal to x naught actually, my bad. But this is just exactly one point. And what point would it be? It would be just f of f of 0 and f dash of 1, which is exactly x naught. So if you want, I can just check that if s is equal to 0, then f of t comma 0, that is just f of 2t for t less than equal to half, and f dash of 2t minus 1 for t greater than equal to half. And for t equal to half, for this is just, let's see, f of 1 equal to f of 0 equal to x naught equal, okay, so I should include this line. I should probably just include this line as well. x1 equal to f of 1 equal to f dash of 0 at t equal to half, and this would be f dash of 2t minus 1 if t greater than equal to half. And if s is equal to 1, so this is just equal to, we see f dash star f at t. If s is equal to 1, we see that f of t comma 0, that is equal to f of 0, which is equal to x naught for t less than equal to 0, which means just t equal to 0, f dash of 1, which is equal to x naught for t greater than equal to 1, and this would be equal to f of let's say what, f of 0 equal to f dash of 1 equal to x naught for t between 0 and 1. So indeed we see that this is equal to the constant map x naught evaluated at t. So this is indeed a homotopy from f dash star f to x naught. So a homotopy like this. Therefore we are finally done. These two classes exactly match, and this is the identity morphism at x naught. Okay, and this is equal to, okay, let's be more pedantic. Why not? I so love to be pedantic. Come on, let's be more and more pedantic. So we see that these two are equal. So for all p from x0 to x1, there exists q from x1 to x0 such that qp is equal to the identity at x0, and pq equal to identity on x1. That is exactly the same proof. I might be pedantic, but I am not a fool, so I'm not going to repeat this proof. So we have found this. Therefore for all p is an isomorphism. Therefore finally we have proven that pi1 of x is a groupoid. Geez, that took a lot of time. That took a hell lot of time. We have got around 50 minutes of time left of the 1 hour that I said. or the 2 hours that I said, in fact. So 1 hour 10 minutes in proving that the fundamental groupoid is a category and it is a groupoid. But now things are simple, because since we have already defined this fundamental groupoid, we know that the automorphism group of each point, or there's a subcategory, or the subcategories of size 1 of this category are exactly groups. So this, we fetch a fact from category theory. We do not need to be this category, we do not need to depend on categories this much, but I'm not really depending, I'm just using them and mentioning them a hell lot of time and pretending that we need category theory for algebraic topology at this point, which we, to be honest, don't. We can do fundamental groups and all of that stuff without any mention of any categories at all, just like all the books did. Moncrief, Hatcher. I'm not really sure about the other books that I have collected, because reading a book takes some time, and I'll be reading them probably today evening or something like that. So I'll see if I go live for that or bother you all for joining. Anyway, so we fetch a fact from category theory. Fact being that one object subgroups of a one object, not subgroups, one object subcategories of a groupoid are groups. So that being said, since all of the morphisms of since all of the morphisms in this groupoid, in this fundamental groupoid, are isomorphisms, we know that the one object subcategories are just that one object, and the Hom set being the endomorphism set. And since all of the morphisms here are isomorphisms, that endomorphism set is exactly the automorphism set. It is in the automorphism group of that object. So yeah, there is that. So yeah, there's this thing that a subcategory of a groupoid is also a groupoid, and since one object subcategories of a groupoid would be a groupoid with one object, there is this joke that was mentioned in Alufi one time, if I'm not mistaken. Then it would be the case that groups are just one object groupoids. A group is a groupoid with a single object. I think this was in Alufi. It was said like that once as a joke. Yeah, definition. A group is a groupoid with a single object. Yeah, that was it. That was joke 1.1. So I'll just read a small part of Alufi for that. It is quite hilarious that how it was put. This is actually perfect viable definitions, since groupoids have been defined already somewhere, but most mathematicians would find it ludicrous to introduce groups in this fashion, or they will at least very politely express doubts on the pedagogical effectiveness of doing so. In order to redeem himself, the author will pass the definition right away to show what exactly it is. If star is a lone object of such a groupoid, then hom G of hom of star and star is the ought of star, because G is a groupoid, and this set carries all the information about G. Call this set G. By the definition of the category, there's an associative operation on G. Okay, and all that jazz. But so yeah, we got the groupoid, the fundamental groupoid. And since one object subcategories are groupoids, we see what are the one object subcategories. These are subcategories with the one object being some kind of a base point x0, and the hom set is just automorphism of x0. So this is really the automorphism of x0 that we are going to focus on. So we actually yeah, okay, let's look at it this way, that okay, so this is the process of what we are doing. We started with the category top of topological spaces. We threw a morphism at the category of all groupoids. Let's say, what is the category of all groupoids called even? It's called just groupoid, or has it some different name or something like that? Let me just look up for a second. Category of all groupoids. Okay, so they could not be more the lack of imagination, the lack of creativity here is just absolutely fabulous. The category of all groupoids are called GRPD, groupoid. Okay, fine, it's fine, we can do with that. So from this we can throw a morphism at the category of groups, GRP. How is so? So this is the morphism pi1. This is the fundamental groupoid. So it sends any space x to its fundamental groupoid pi1 of x. Now in GRP, what we do is we select just one object at a time. So what we do is we just, I don't know what to call this morphism. This just selects one object. Excuse me for my naivety, but I have no idea what to call this. This just selects one object and sends it to a group. So what would this group be called? So pick some object x0 and we send this to the group ought of x0. Ought at where? Ought at pi1 of x of x0, and that is what we call the fundamental group of x1 based at x0, right? Now you might be aware of another process of getting at this whatever this fundamental groupoid is, that is to uh, to get a functor here from top to top star, not just to top star, not actually just to top star, to where actually, to some kind of a power category of top star. So it is some kind of a power category of top star. I'm not really sure how that works, or how the morphisms would work between them. But yeah, this is not really functor. This is not really functor. From we select one object here, and similarly we would like to just select one object here. Okay. So having selected one object, what we get is a subcategory of top star. It is a subcategory of top star, which I would like to call top star of X. So what is this subcategory? This subcategory has objects looking like this, x comma x naught, such that x naught is a point in X. So that is what this subcategory looks like. You just select one object X, and in this category we just look at all pointed sets, or all pointed spaces of this form. So x comma x naught, we look at this, we look at x comma x1, x comma x whatever, something like that. We look at all pointed categories like that, pointed topological spaces like that. And from this there is this functor. In fact, in general, from not really from here, in general from top star itself, we have a functor to groups called the fundamental group functor. So what this does is that it takes a pointed space and sends it to its fundamental group, like that. So yeah, that is what there is. There is the fundamental groupoid, and from that we extract this fundamental group. So just for the lack of something else better to do, we just look at what the fundamental group is right now, like right now. This is sloppy notation. This is quite a sloppy notation, but you cannot be pedantic all the time. For any x comma x naught in top star, we have a group called pi1 of x comma x naught in GRP. This pi1 is a functor. Okay. Such that what? Such that something particular happens, which is just just give me a moment to phrase this. So since we have path homotopy in the category of topological spaces, or path homotopy for topological spaces, we can have loop homotopy for pointed topological spaces. So what is a loop? A loop is uh, L from, let's call this a map from a circle to this pointed topological space, such that L of, zero as in, okay, yeah, let's throw that out. Oh, actually, it's not that bad of an idea. Just define a pointed circle. So you have a circle, you take a point here. Okay, yeah, that makes complete sense. A loop L is a map in top star. So what is this loop L? Loop L is a member of the Hom set in top star from where to where? From S1, 0, from this space to x, x naught. Yeah, I'm happy with that definition. Now, what does this really mean? This means loop L is a map from S1 to X such that L of 0 is x naught. This is we are talking in top, and this we are talking in top star. Choose what you like. Similarly, you can say that loop is map from I to X such that L of 0 equal to L of 1 equal to x naught. But then you have to see this diagram where I is basically, where S1 is basically the identification of I, and I along with these points, let's say I comma, I comma 0 is a fine pointed space, a very nice pointed space. S1 comma 0, that is one thing. So yeah, this does well. This does well. That L of, similarly I comma 1 is also here, that with the same identification and the same map. This entire diagram commutes. So we can define a loop like that. And this thing, the loop space of a point for x naught in X, we define L is not really map here. Yeah, L is actually a map here, not a problem. L is a map here. What is it? Just hold up a second. Just hold up a second. Okay. So the top star is the category of pointed topological spaces with base point preserving maps. Yeah, it has nothing to do with homotopy. Yeah. We define this fancy name loop space of x naught to be omega of x comma x naught. This is again, as you can guess, some kind of a functor, right? This is some kind of a functor. This omega x naught, it is, well, actually this is the set of all loops from I to, I'll just be as coarse as possible in this definition such that I can be as elegant as possible in the next one. So this is the set of all loops like that. Let's see even write continuous. Why not? We are being coarse here. So this is, check this out. This loop space is hom top star from S1 pointed at 0 to x pointed at x naught. How is that? So omega, let's see, let's check this functor out. Omega is this functor. This is the loop space functor. We take any we take any pointed topological space, and what do we actually return? We return a set of maps, right? We return a set of maps. You know what? This is not very helpful. You know what is helpful? Is defining omega to be a functor from not exactly omega. Well, let's define small omega. This is not really helpful. Not helpful at all. What we can do is we can take this, let's shrink this notation a bit. S1 we always point at 0, so no problems. We can take this, we can quotient this by path homotopy, right? And this gives us all homotopy classes of loops based at x naught. Very nice. So what we can do is that we can define omega, this omega to be a functor. We can define this functor omega from top star, the star is at a wrong position here, top star to, I think it should be GRP. Yeah. So finally we have this fundamental groupoid functor, and at this point we can just do with this. Call this pi1. Okay? And pi1 of x comma x naught is hom S1 to x comma x naught quotiented by path homotopy. Take some time to digest that, I guess. So we define loop homotopy and the fundamental group in two possible ways. One is we form the loop space and we quotient the Hom set, or the like the second Hom functor, we quotient that by the homotopy equivalence. The homotopy is an equivalence on two things. Homotopy is an equivalence on the morphism class, if we take the other definition of a category. So what is homotopy and equivalence on what set or class is homotopy and equivalence? One thing is that homotopy is an equivalence or on the morphism class of top, right? Is it? Yeah, homotopy is an equivalence on the morphism class of top. What else is it can be an equivalence on? It can be an equivalence on the object class of top, as in the space homotopy or the homotopy of topological spaces. It can be on morphisms on the discrete top star. So in this category, in this delta top star, we remove all the in between morphisms and we consider only endomorphisms. So this is just the union of all the endomorphism sets of x comma x naught, or let's call this end of A, says that A is in a top star, or A is an object of top star. So this can be seen in that. Homotopy can equivalences on these things. Homotopy is an equivalence on these things. So that is there. What else is to be done? In fact, we get a homotopy class of F. We get operation on a homotopy class. We get the fundamental groupoid. Hatcher proves that this is a it is a group. It is a quite a long proof. What is this, by the way? Okay. So there are many other ways of looking at this object, the fundamental group of a pointed topological space. What we can say is that if the space X is path connected, then this uh, then basically all the fundamental groups built on that space are isomorphic. We can, yeah, we can say that from a rather naive construction. And sometimes these more naive constructions are better in a way that you can very easily incorporate other ideas, like very different ideas from very different sources into them, because they don't take into account very heavy machinery. As in, if suppose this fundamental groupoid approach that took up a huge amount of machinery, and so did this loop space and all this Homset quotient thing and this weird kind of a functor. But if you just keep the amount of machinery to a bare minimum, you just form the quotient, you just take the equivalence classes of all maps, or just the homotopy of paths. If you just consider the homotopy of paths, then it is easy to see that you can incorporate various ideas such as connectedness and compactness into this business. And one result from that is, if X is path connected, then pi 1 of x comma x1 is isomorphic to pi 1 of x comma x2 for all x1 and x2 in X. So one way of one more natural way of rephrasing it would be something like this. If there is a path, is there any better way of putting it? Yeah, first let's say this. If there is a path from x0 to x1, then pi 1 of x comma x0 is isomorphic to pi 1 of x comma x1, right? Now phrase it like this. If there is some p, check this out, in the Homset of this fundamental groupoid of these two, let's see, x0 and x1, if there is a path in this, that is, this is not empty, then pi 1 of x comma x0 is isomorphic to pi 1 of x comma x1. Now check this out. What is pi 1? It is the automorphism group in the fundamental groupoid pi 1x of this point x0, and pi similarly this is the automorphism group at inside the fundamental groupoid category of this x1, and we say these two are isomorphic. And what does this say? This says that since we know that pi 1 of x is a groupoid, we know that if the Homset of these two are non-empty, so this means this said if x0 is isomorphic to s1 in this category, in this fundamental groupoid as objects if x0 and x1 are isomorphic, that is there is a path between them, then ought of x0 is isomorphic to ought of x1 in that basically in that same category of pi1 of x. So if you take this path, if you take this groupoid path, select one object and consider the automorphism, then this is an entirely trivial fact. In fact, there is a functor, right? This thing which sends x0 to pi1 of x comma x0 from this fundamental groupoid pi1 of x to grp. This is a functor, and a functor must send isomorphic objects to isomorphic objects, and therefore this is clear that if x0 and x1 are isomorphic in the fundamental groupoid, which means the same thing as there being a path from x0 to x1, then we see that the image of the functor, they are also isomorphic, as in the fundamental group based on those two base points x0 and x1 are isomorphic as well. So this fact, which would require some kind of a argument that there is a path like this, say there is a path from I to x such that f of 0 equals x0 and f of 1 equals x1. If there is a path like this, then there is a inverse path like that such that this is equal to f of 1 minus t f of t. There's an inverse path like that, and so for any other path here, so not like that actually, for any loop based on x0, you can extend this loop to be let's see, from x1 you draw a path to x0, then you do the loop, then you go back by the path, and that is essentially a loop on x1. So this gives that each loop based on x0 corresponds to a loop based on x1. That is all nice and dandy, but that is a lot of arguments, and here you get a minimal amount of arguments. You show that this fundamental groupoid exists, this is a groupoid, so you transfer to the groupoid category, then you take a functor, and since this is entirely a categorical fact, this comes from an entirely different thing which is well verified, and it is a categorical fact. It is almost a foundational fact that isomorphic objects are sent to isomorphic objects by any functor. You conclude the same trivial fact that if there is a path between two base points, then those two base points give rise to the same fundamental group. So yeah, this is one way of looking at things, and I kind of like this approach, to be frank, but this is not at all any kind of an alternative to, let's say, we ignore the other approach. We cannot ignore the fact that all of these things are constructed like that. We cannot ignore the construction, but we can ignore what we can do is move towards a more elegant language, a more elegant approach from this construction. But that thing in itself feels kind of, let's see how to put it, that thing feels kind of it feels kind of contrived that you start off with one approach of looking at things and then you look at other approach, but that is entirely pedagogical, and in pedagogy just if you get used to something, you get used to that thing. So I guess it is not much of a problem. And since all logical truths are isomorphic and all logical falsities are isomorphic, we do not really need to care how we arrive at one, which one we start at, which one we end at, because they are all, at the end of the day, logical truths. So, yeah, you move from one belief, one viewpoint to another, and that is, and you do some nice maths on the way. That is, I guess, one good viewpoint towards life. I hope so. Okay, a space is simply connected if and only if there is a unique homotopy class. A space is simply connected if it is path connected and has a trivial fundamental group. A space is simply connected if and only if there is a unique homotopy class of paths connecting any 2 points in X. Okay. That's great. So there's a simply connected thing, but I guess it is getting a bit late. It is 1 already. I should probably go for lunch. Or maybe I can go later, a bit later. Then we get fundamental group of the circle. Evenly covered. Are we dealing with covering spaces here? God, then we get a huge number of applications. This is a fundamental theorem of algebra. We get Brouwer's fixed point theorem, continuous map from the Borsuk-Ulam theorem, is it called? Yeah, it is the Borsuk-Ulam theorem in dimension 2. Okay. Then we get fundamental groups of product spaces. Induced homomorphisms after that. So after that, Hansel really starts talking about the functor, but he does not talk about the functor. He talks about just the consequences of that fundamental group being a functor. So that is, I think we can cover that after in the evening or something like that. I should really probably just go now. Okay, so we got simply connectedness, the fundamental group. So we'll be looking at the fundamental group, simply connectedness, fundamental group of the circle. Yeah, then covering spaces. This I guess we can look at this in the evening. Yeah, in the pre-dinner session, I hope we'll be looking at this. So yeah, I guess that is it for now. We had a good time, and it is, well, nice time to end it, shall we?